Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today's session we like to discuss about quiz 2 problem for section number 5 as requested by one of you. Okay, I'd like to show you how this problem can be solved, and from my observation based on the submitted answer, most of you managed to understand the concept well, so that's good news to me. So anyhow, I'm going to show you the solution based on my interpretation. So hopefully you all guys do agree with my suggestions, because in EMT the way you solve the problem based on usually our interpretation and how convincing we can state our answer is usually the case here. Okay, so let's recap the question. Okay, the question as shown here, number 14. Okay, given here three concentric spherical shell are the radius equal to 1, 2 and 3 meter respectively, have charge distributions 2, -4, 5 millicoulomb per meter squared. So please be clear here that the charge given here is not total charge, as some of you did suggest in your solution. It's actually charge density, and which type of charge density based on the unit given here, it is they are surface charge. So that's how you determine the type of charge given in the problem. So for part 1, calculate the flux through two radius, r equal to 1.5 and r equal to 2.5 meter. So let's draw the problem first. Okay, so I'm going to draw three spherical shell here. So this should be my shell number 1, having radius 1 and charge density rho s 1. Then I'm going to draw my second spherical shell. So concentric meaning that all the three shells having the same center. So that's what it meant by concentric. So this having the radius 2 and charge density, now I'm going to denote as rho s2. And finally the outer shell. So that should denote as radius 3, and I'm going to label the charge density as rho s subscript 3. So that should be the first attempt that I always try to draw the suitable diagram representing the problem. So for number 1, so what should be the flux electric? Okay, at two location, radius r equal to 1.5 meter and r equal to 2.5 meter. Okay. So what I'm going to do now, I'm going to think about the idea of solving the problem. So usually what I always try to think here, I'm going to state to myself what are the input given by the question and what are the output given by the question. What the required answer from the given information from the question. So what given here, rho charge or charge density, and what requested for us to determine now are the electric flux. So what I have to do now, I have to think about the method I can link these two parameters together. So what should be the suitable method to obtain flux from the charge? And we have been informed about Faraday postulates. Okay, what does this statement meant that, remember that we are saying the number of line is equal to the charge. So this is what we stated earlier in our discussion. So please remember the first idea when I talk about electric flux, I mentioned about electric flux is representation of line coming out from the charge or from the source, and the way we visualize the line actually is similar to the amount of magnitude of the charge from that particular sources. Okay, let's show now where is R equal to 1.5. So R equal to 1.5 should be located here in this particular region. So this should be our interested surface. So this given as 1.5. So from the diagram I can see that using this argument, flux electric at 1.5 should be equal to the charge. So what meant here, the charge contained by this imaginary surface, and you can see the charge contained by this particular imaginary surface is only represented by the surface charge density located at the spherical shell of radius r equal to 1. So this should be our sample of source. So we are saying that should be the integration of the dq. And this dq is represented on our diagram as shown here. And we know that based on our model of charge, for surface charge should be equal to the rho s, but we can see the rho s here specifically refers to this particular nomination, should be rho s1, and based on our ds spherical coordinate system that we can refer to table of handout number 2, that should be given as the radius, and we know the radius here should be 1. Okay, r squared d theta d phi. Okay, and we have to integrate twice, theta from 0 to pi, phi from 0 to 2 pi. And we do the mathematics, it's going to give you what is, because the rho s1 value is equal to what? Anyone can state what should be the rho s1 value? 2 millicoulomb per meter squared. Okay, so I'm going to write here, sorry about overcrowding of the labeling here, 2 millicoulomb per meter squared. So now what we're going to have, 2 times 10 to minus 3, because we have to convert into meter, and then that should be our rho s, done, and then 1 square, and that should be multiplied by 4 pi. So that should be our solution. Remember the unit here should be coulombs. Okay, that should be the flux measured at the radius of r equal to 1.5. So alhamdulillah, we have solved for this problem. Let's proceed for the second one here just to test our understanding. So where is r equal to 2.5? So let's draw that position on our diagram. Should be between 2 and 3, so should be this. Look, so this should be our imaginary surface that we're going to calculate the flux. Okay. So the radius now given as 2.5. So again, so for flux electric at r equal to 2.5 now, so I'm going to look for the charge confined by that imaginary surface. And we can see now there are two charges enclosed by this particular surface. They are, the first one shown here, and the second one shown here. So let's denote this as dq1, and this one we label it to be dq number 2, and therefore should be equal to dq1 plus dq2, and we can see that the dq1 can be extracted the value from the above solution, and you have to calculate the dq2 using the same method as shown above, but the only difference, you have to change the value of rho s2, and then you have to change the value of the radius, because for the sample number 2, it exists on a sphere having radius r equal to 2 meter. So therefore you have to convert 1 to become 2 in order to fulfill the requirement of parameter dq number 2. So with that, alhamdulillah, we have completed for part 1 of the problem. Okay, so let's do for the part 2 now. I'm going to show you only one. Hopefully from the others you can see it's similar. So let's repeat for, I'm going to find for d equal to r 0.5, and let's make it both cases. We're going to focus for radius r equal to 0.5 and r equal to 3.5. Okay, let's do that. So for this one, you might try yourself and just to ensure that you do understand the concept clearly, because what is important by doing the quizzes, the problem from the handout, for you to understand the concept. The solution is not that critical, because once you obtain the correct concept, inshallah, usually the solution going to be alright. Okay, let's find the D. So D is known as electric flux, electric field density. Okay, so I'm going to use this. So number part 2 now. Okay, so D. So D, remember, is known as electric field density in our case, or sometimes people also denote it to be electric flux density. So how we solve this problem? Again, so what we do have now, the input and the output. The input to this problem, again, charge distribution, and the output is D. Okay, that should be what I'm going to think. Now, how do I able to link these two parameters together? Okay, we've been informed that I can find D from charge by using Gauss law, or I can use another method, finding first the E. E is known as electric field intensity. Then from E we can convert into D using the medium, and in this case the medium assumed to be free space. So finding E from rho s, we can use Coulomb's law. But given a chance, we would like to use Gauss law. So Gauss law is much preferred compared to Coulomb's law because it's easier. So but Gauss law can only be used in certain conditions, and looking at the source distribution in this problem, we can use Gauss law. So therefore Gauss law can be used for this particular problem. So in Gauss law, remember, we always have systematic approach, first by choosing the coordinate based on the problem or charge distribution. The coordinate that we should use here should be spherical. Then we're going to label the regions, and we can see there are 3 distinct regions that we can observe: region number 1, region number 2, or 4 regions actually, region number 3, and region number 4. There are 4 distinct regions that we can classify from our diagram. Okay, 4 different regions: region 1, region 2, and then step number 3, we're going to focus on specific region. Okay, so let's see now. The question asks for the D at R equal to 0.5. Okay, so and then by observation we can see r equal to 0.5 located in this region. So therefore we can say this is actually the D in region number 1. Okay, so D in region number 1. So let's draw our interest point. So here, region number 1. So we have to identify the position in our diagram for where the D that we want to actually determine. So for first part of the question, find D at R equal to 0.5. Therefore, I'm going to draw it to be here, and then I found it to be located in region number 1. So then I'm going to draw my Gaussian profile. So Gaussian profile must be completely closed, and the second characteristic must passing through the point where you want to determine the D. So I'm going to draw my Gaussian. So this should be my Gaussian. Okay, and then we know that this should be 0.5 because specifically given by the question. But you want to make it general, we can just set equal to R, and R is smaller than 1. So let's proceed now. We have drawn the Gaussian profile. So what Gauss law state next? We have to solve the mathematics. The mathematics state that Gauss law state D dot ds should be equal to Q enclosed. Okay, that's typical Gauss law that we have to use. And then remember, this particular part of the equation must refer to the actual shape of our Gaussian profile, and this should be referred to what we shown here, the red structure. And then by doing the proper mathematical solution, you're going to end with dr 4 pi r squared. And remember, now we can substitute the r squared with 0.5 because we want to obtain at that position only. Okay, that's done. So now we're going to go to the second part of Gauss law. What should be the enclosed charge? And from the observation that we can see here, there is no charge confined by that Gaussian, because the charge that appear to be nearby is actually on the surface of R equal to 1. And 1 is actually bigger than 0.5, and there's nothing, no charge within the region less than 0.5 or less than 1. So therefore, it's going to be 0. Then straightly we can conclude that D for R equal to 0.5 equal to 0. That should be the solution that we should have for that particular position. Okay. Okay, let's try with the next one. What should be the D and R equal to 3.5? Okay, so let's do that. So what should be the D at R equal to 3.5 meter? So that should be the next logical problem I'm going to solve now. So again, where is my 3.5? Should be bigger than 3, so I'm going to draw it to be here. And I can see that by making the position to be here, it's actually in region number 4. So I'm going to say, this particular problem located in my region number 4, because bigger than 3 meter. So again, what we have to do as before, we're going to draw the Gaussian. Okay, and then this Gaussian having radius 3.5, and then we have to solve the mathematics. What is it? Gauss law said D dot ds must be equal to Q enclosed Okay, and then from the left hand side, we're going to use the typical solution that we always observe regarding this structure. dr 4 pi r squared, and now we're going to replace r squared here with 3.5 because the question specifically asks at that particular radius, and then the Q enclosed. So you can see it's repetition now what actually charge contained by that particular Gaussian profile, and we can observe again there are three charges, one to be here, one to be at this location, and the last one to be here. So I'm going to use the previous level, dq1, dq2, and dq3, because why? We can see from our observation all the three charges actually confined by our Gaussian profile, which is located at r equal to 3.5. So now using a typical method that we observed before should be dq1 plus dq2 plus dq3, and by solving this mathematics as what you have solved above, just the only difference you add another term here and then divide everything by 4 pi, then you're going to get your actual D result for this particular position. So again, what you can see solving problem, you must actually know the principle how to actually solve the problem. So this is important. Before you proceed solving the problem, you must think the method that you want to adopt in solving the problem. And those methods actually relate to the issue that we discussed in our lecture. And also knowing this method is important as well for you to able to answer well in your test number 1 that will coming very, very soon. With that, thank you for your attention. Inshallah, we're going to see again in our next video.